I'd like to start with a couple of quick examples. These are spinneret glands on the abdomen of a spider. They produce 6 different types of silk, which are spun together into a fiber tougher than any fiber humans have ever made. The nearest we've come is with aramid fiber. And to make that, it involves extremes of temperature, extremes of pressure, and loads of pollution. And yet the spider manages to do it at ambient temperature and pressure with raw materials of dead flies and water. It does suggest we've still got a bit to learn. This beetle can detect a forest fire at 80 kilometers away. That's roughly 10,000 times the range of man-made fire detectors. And what's more, this guy doesn't need a wire connecting it all the way back to a power station burning fossil fuels. So these 2 examples give a sense of what biomimicry could deliver. If we could learn to make things and do things the way nature does, we could achieve factor 10, factor 100, maybe even factor 1,000 savings in resource and energy use. And if we're to make progress with the sustainability revolution, I believe there are 3 really big changes we need to bring about. Firstly, radical increases in resource efficiency. Secondly, shifting from a linear, wasteful, polluting way of using resources to a closed-loop model. And thirdly, changing from a fossil fuel economy to a solar economy. And for all 3 of these, I believe biomimicry has a lot of the solutions that we're going to need. You could look at nature as being like a catalogue of products, and all of those have benefited from a 3.8 billion year research and development period. And given that level of investment, it kind of makes sense to use it. So I'm going to talk about some projects that have explored these ideas. And let's start with radical increases in resource efficiency. When we were working on the Eden project, we had to create a very large greenhouse in a site that was not only irregular, but it was continually changing because it was still being quarried. It was a hell of a challenge, and it was actually examples from biology that provide a lot of the clues. So, for instance, it was soap bubbles that helped us generate a building form that would work regardless of the final ground levels. Studying pollen grains and radiolaria and carbon molecules helped us devise the most efficient structural solution using hexagons and pentagons. The next move was that we wanted to try and maximize the size of those hexagons. And to do that, we had to find an alternative to glass, which is really very limited in terms of its unit sizes. And in nature, there are lots of examples of very efficient structures based on pressurized membranes. So we started exploring this material called ETFE. It's a high-strength polymer. And what you do is you put it together in 3 layers, you weld it around the edge, and then you inflate it. And the great thing about this stuff was that you could make it in units, so roughly 7 times the size of glass, and it was only 1% of the weight of double glazing. So that was a factor 100 saving. And what we found is that we got into a kind of positive cycle in which one breakthrough facilitated another. So with such large, lightweight pillows, we had much less steel. With less steel, we were getting more sunlight in, which meant we didn't have to put as much extra heat in winter. And with less overall weight in the superstructure, there were big savings in the foundations. And at the end of the project, we worked out that the weight of that superstructure was actually less than the weight of the air inside the building. So I think the Eden project is a fairly good example of how ideas from biology can lead to radical increases in resource efficiency, delivering the same function, but with a fraction of the resource input. And actually, there are loads of examples in nature that you could turn to for similar solutions. So, for instance, you could develop super efficient roof structures based on giant Amazon water lilies, whole buildings inspired by abalone shells, super lightweight bridges inspired by plant cells. There's a world of beauty and efficiency to explore here, using nature as a design tool. So now I want to go on to talking about the linear to closed loop idea. The way we tend to use resources is we extract them, we turn them into short-life products, and then dispose of them. Nature works very differently. In ecosystems, the waste from one organism becomes the nutrient for something else in that system. And there are some examples of projects that have deliberately tried to mimic ecosystems. And one of my favorites is called the Cardboard to Caviar project by Graham Wiles. And in their area, they had quite a lot of shops and restaurants that were producing lots of food, cardboard, and plastic waste that was ending up in landfill. Now, the really clever bit is what they did with the cardboard waste. And I'm just going to talk through this with this animation. So they were paid to collect it from the restaurants. They then shredded the cardboard and sold it to equestrian centers as horse bedding. When that was soiled, they were paid again to collect it. They put it into worm recomposting systems, which produced a lot of worms, which they fed to Siberian sturgeon, which produced caviar, which they sold back to the restaurants. So it transformed a linear process into a closed-loop model, and it created more value in the process. Graham Wiles has continued to add more and more elements to this, turning waste streams into schemes that create value. And just as natural systems tend to increase in diversity and resilience over time, there's a real sense with this project that the number of possibilities just continue increasing. And I know it's a quirky example, but I think the implications of this are quite radical, because it suggests that we could actually transform a big problem, waste, into a massive opportunity. And particularly in cities, we could look at the whole metabolism of cities and look at those as opportunities. And that's what we're doing on the next project I'm going to talk about, the Mobius project, where we're trying to bring together a number of activities all within one building so that the waste from one can become the nutrient for another. And the kind of elements I'm talking about are, firstly, we have a restaurant inside a productive greenhouse, a bit like this one in Amsterdam called De Cas. Then we would have an anaerobic digester which could deal with all the biodegradable waste from the local area, turning that into heat for the greenhouse and electricity to feed back into the grid. We'd have a water treatment system, treating wastewater, turning that into fresh water and generating energy from the solids, using just plants